Hey, welcome to CS 1187, sometimes known as Math 1187, sometimes known as discrete structures, and it's all of the above. It's an interesting situation here because I'm a math professor, but I've been doing computing for, you can tell how old I am, since I was a kid. And I've developed my ideas about computing as ideas about computing have developed. And in fact, computing has become more a part of my math as time goes on. So it's an interesting situation. This is a more abstract course, and I have to say from the get go, this is not a programming course. Well, if it's not a programming course, what's it doing as a computer science course? And this is the part that's been missing from what you've studied so far. It used to be that what we call computer science now was called data processing. And that's really where it all began with the IBM punch card machines and the like. Some of those ideas are still in use now. They seem old, but they're actually very contemporary. And the focus here for this course is on data. Data is, it's not worth writing a program if you don't have the data to work with and you don't really understand how to work with that data. And so, what we need to be able to do in computer science and in applications is describe data, manipulate data, see the structures in data, impose structures on data, access data, see patterns in data. Well, I think you see the pattern now. What we're studying here is more about data than it is about the programming. So the programming basics that you've studied so far are very important, but you got to have something to do it with. Over the years, this has changed quite a bit because the amount of data that we have available is so much more extensive than it was when, even a couple of years ago. I was going to say when I started, but that was a long time ago. Even a couple of years ago, we had much less data, and so many of the things that people do with computing and applications is work with data. So what we're going to do is start working with data, develop language to talk about data, develop ideas that manipulate data, and then start to see what the structures are. So that's the structure of the course. On an administrative note, we're not going to have set meeting times. I'm going to make lectures like this, and you're going to watch them. And if you want, you can watch them over, and I'll post notes. And we do have a textbook. The link is on the Moodle site, and the textbook has it's pretty good as far as textbook goes. So let me kind of get us going. Here we are. We're talking about data and sets, and that's what we're going to do. And I'm going to start off with some kind of natural examples. Some people would say natural language, but these are just things that might happen. Oh, I don't know. I've been watching a little bit too much Law and Order over the break. And so someone could look for, hey, we found we had a blue car and the license plate ended in 3-4. So we had a blue car and the license plate ends in 3-4. And that seems to me like a pretty natural question to be asking in all kinds of contexts. I mean, it might be, it might be something about a planet that has a certain property, or the list of planets that have a certain property, list of airplanes that have a certain property, list of crops that can thrive only at a certain elevation. This is what we do with data. So this is a natural thing to do, and this corresponds to the abstract idea of intersection. We've got two properties that we want to see the things that have both. So the natural word that goes with this is and. So the car is blue and the license plate ends in 34. And so that's a thing that people would naturally want to do with data. And so this corresponds to an idea of intersection. That's the fancy mathematical term for, hey, we got a blue car, ends in 3 4. We better go through all the list of registrations and so forth and so on. There are other things that you can do with this kind of operation. We could say, hey, here we are in southeast Idaho, where the license plates have a county designator and then a number, and we're in southeast Idaho, so we're interested in cars whose plates start with 1B, that's Bannock County, or 4B, that's Bingham County. So we want any car that is registered either in Bannock County or Bingham County. That's a perfectly natural thing to be asking about, and that corresponds to the set theory idea of union, and the natural word that goes with that is or. And so here's another concept, a very natural concept that we're going to abstract and then use in the abstract sense. I'm going to interrupt here. Why are we interested in abstraction? The reason that we're interested in abstraction is there's all kinds of data out there that we haven't thought of yet, or we haven't been exposed to yet, or hasn't even existed yet. And so we want to be prepared in the abstract to deal with any data that might come along from whatever source and be able to have tools that we can apply to help us study and understand that data. So abstraction really works. We're not here to talk about cars. I kind of like cars. We're not here to talk about cars. We're here to talk about the ways that people can use data about cars, and it's the ways, not the cars. Okay, here's another one that is kind of a natural kind of question. Here, this is a little bit of a quiz. Let's look for drivers who have a commercial driver's license and they're an organ donor. So in Idaho, here you get a thing on your license that says you're an organ donor. A lot of people have commercial driver's licenses. And so when we're looking at this, the key word is and that tells us it's intersection. So I'm going to introduce the symbol for intersection. It's this upside down U, no serif or anything. And while we're at it, let's go back and do the symbol for union, which is a U. It's meant to be abstract. It's meant to be kind of plain and simple. Okay. So one more set operation that's pretty natural. We want all the Toyotas that aren't red. It takes a long time to write out. That's another reason why we want to have abstract notation, is so that we can do this. So we want all the Toyotas that aren't red. Well, we want to look at all the Toyotas, but we want to throw away the ones that are red. Not throw them away in the sense of sending them to the junkyard, but as far as whatever it is that we're looking for, we want to have these non-red ones. So this is the set theoretic difference. And the symbol for that, while we're doing symbols, is a backslash. So here's our Toyotas. They're not red. Difference and backslash. Okay. So what we want to do is apply this to something more general than cars. And the most general thing that we can do is to apply them to sets. And so what we need to do is introduce the idea of a set, and then as we continue, we'll be doing these operations with sets. There's one I've left out that's very important, but we'll get to that in the next video. Okay, so sets. There are a bunch of different ways to specify sets. Now, if you go to a mathematical conference and say to the guys with the beards, I used to have a beard, but I shaved it for COVID. If you say to the guys with the beards and the tweed jackets and say, well, what is a set? And they'll go, well, this is a very difficult question that no one really seems to understand. In computing, we have a good idea what a set is. And so a set is, everyone says a collection of stuff. It's a bunch of stuff. We have the set of cars in Idaho. It's not that mysterious. If you start to get to infinite things, then it starts to get much more mysterious. But we have very limited ability to compute with infinite things, and so computationally, that's not so relevant. Um, Many of the concepts go through, many don't. Okay, so I'm going to give you some ways to talk about a set, and then we can start to manipulate them more generally. The tradition is that sets are denoted with capital letters, and so I'm going to have a set with the capital letters. And the other tradition is, and this is pretty universal in all of the earthbound languages, is that sets are denoted by using curly brackets. And so that's something that's built into all the keyboards. And so I'm going to write down a set. And the elements are called elements. Some people call them atoms. And so what I've done is taken a list of numbers, 8675309, and put them between curly brackets, and that's a set. So the elements are things that are in there. So 12 is not in here, 2 is not in here, 5 is in here, 0 is in here, and that's that. One important thing about sets is there is no order, and so I'm going to write another thing here, and then I'll explain to you what I've done. I believe I've done this correctly. The same digits in a different order. Those sets are equal. Set equality means that the two sets have exactly the same elements. And then we got a 0 over here, and we got a 0 over here, and we got a 9 over here, and we got a 9 over here, and we got a 7 over here, and we got a 7 over here. And so those are the same sets. The cardinality, that's a big word for number here, is 7. And so this is a set with 7 elements. And that's the big fancy word is cardinality there. Okay. So this is one way to specify a set. It's called the roster. It's like, as I was getting ready for this, I was looking through the class list on BangleWeb, and that's a roster. That's the set of students who are enrolled in this course. People try to make it mysterious, but I don't think it's all that mysterious. But you never know what people think. Okay. There's another kind of way of specifying a set, and I'm going to do a very specific example. And this is pretty common. So I'm going to call this set B, just for no particular reason. It's our second set. And it's the set of all things of the form 2n, where n is an integer. So that happens to be an infinite set, and which doesn't trouble us for right now. But this is called set builder notation, because what it does is it gives you a recipe for building the set. And so I'm going to take an integer and multiply it by 2, and I'll get an element of the set. So we have that, say 6 is in B because it's 2 times 3. And 7 is not in B because 7 over 2 is not an integer. So admittedly, this is more abstract, but that's the situation here. By the way, don't get too worried about what's going on here. I'm going to scan this and put it up on Moodle, so don't worry too much about that. So that's a common way to specify a set. Some of the software that is available, you'll read about this in the textbook Doran Levasseur. SageMath is probably the one that is most likely to be the most useful for you. Tends to use set builder notation, so that's a good way. So we're just going to specify. Now, and there are a lot of things that happen in computing, like with languages and more abstract recursive functions and things like that, that are really constructed in this set builder way. So this is a good way to do things. So the final example for today is I'll call this set C, and it's the I better write it down and then I'll explain what's going on. So here's the notation. You know it's a set because it's in curly brackets, and it's the set of all x, and this colon is read as, it depends on whether you're being pretentious or not. Some people say that is such that. That's kind of an abstract, bizarre phrase. So I sometimes prefer to say with the property P. So P is a property. This is a statement about X that is either true or false. If P is true, then X is in the set. If P is false, then X is not in the set. And so this is a proposition. We're going to spend a lot more time talking about these propositions as the semester goes on, because one of the things that we're supposed to study is logic, which is the study of how you combine propositions. And so this is all going to make much more sense as we go on. So we could say almost, you can pick up any kind of test that you would like for something to be in a set. So for example, you could talk about a number, an integer is in a set if it's even. That's actually the same set that we just talked about before, specified differently, but that's a test. So you say, oh, 6 is in there because 6 is even. 7 is not in there because 7 is not even, and so you can apply the test. Some of these tests can get to be rather complicated, so we're going to build up our way of looking at these things. So let me just write this out. And so those are our set notations. So here I've got the example proposition P of X. Is X even? Yes. Oh, it's in. Is X even? No. Well, go away. Here, don't get behind the velvet rope. And so that's the introduction to sets. By having this abstract way of talking about things, we can look at new types of data that we haven't even dreamed of yet, and we'll be able to manipulate them and access them and find patterns in them. And that's where this all comes about. So you're going to read about this in Dore and Levasseur, and we're going to practice with it. And then you're going to use this as a way to specify things about data for the rest of your life, because we're going to compute for the rest of our lives, aren't we? So talk to you soon.